Can you turn basic lead into solid gold? Ancient alchemists tried for centuries and failed. But today, inside high-energy particle accelerators, we can actually achieve this through nuclear transmutation. The identity of any element is defined by one absolute rule: the exact number of protons in its nucleus. Alter the proton count and you change the element completely. But if you add or remove too many neutrons, the element stays the same, but its core becomes highly unstable. It becomes a radioactive isotope. To regain stability, it undergoes radioactive decay, emitting alpha, beta or gamma radiation. Through this process, it eventually transmutes into a different element over its half-life. However, as electrical engineers, we do not alter the nucleus. To us, that heavy core is just a massive anchor locked in place. Our true domain is governed by the tiny, almost weightless particles orbiting on the outside, the electrons. It is their freedom that builds our modern world. But why do electrons flow so easily in copper, yet remains completely trapped in wood? Welcome to VastVoltage. Let's visualize the invisible. Let's examine a single atom of copper. While its true state is a complex quantum cloud, the classic planetary model works perfectly to explain the engineering. Notice the outermost electron. In metals like copper, this valence electron is so loosely bound that it naturally breaks free from its parent atom. Once it departs, the electrical balance is broken. The atom is missing a negative charge, leaving behind a positive ion. But atoms in a metal do not sit alone. Let's zoom out. Billions of these positive copper ions lock together in a massive 3D grid. We call this a crystalline lattice. They are held together by a shared ocean of these free electrons, the metallic bond. Zoom out more and these continuous grids form microscopic grains, connected at grain boundaries like a 3D puzzle. Zoom out one last time and you hold a solid copper wire in your hand. Yet, this solid wire is never completely still. The atoms constantly vibrate in place. This microscopic motion is exactly what we measure as heat. This microscopic vibration isn't just about temperature. It creates a physical obstacle for electricity. As the ions bounce more, they increase the chances of a free electron crashing into them. This is called electron scattering. It's the fundamental reason why a hot wire has more electrical resistance than a cold one. If you apply intense thermal energy, they vibrate so violently that the crystalline lattice shatters. The solid copper melts into a liquid. Add even more energy and the metal boils. It vaporizes into a glowing metallic gas, expanding into space. But to push an electric signal smoothly across an entire city, we need stability. We need the cold, solid grid. So why does an electric signal move so easily through a copper grid, but stops if it hits a piece of wood? To visualize this, let's look at an atom of carbon, the main building block of wood. Carbon has 6 electrons, but the 4 of the outermost layer are the ones that define its behavior. These outer electrons exist in what we call the valence band. Above this energy level is the conduction band, a state where electrons are no longer tied to a single nucleus. If an electron reaches this band, it becomes free to move through the whole material. But in insulators, like wood, glass or plastic, there is a large energy difference between these two states. This is the band gap. The electrons in the valence band lack the energy to move across this gap. They stay fixed in their positions. Every insulator has a breaking point, known as its dielectric strength. For dry air, this limit is approximately 30,000 volts per centimeter. For solid insulators like glass or specialized plastics, it is significantly higher. Once you cross this threshold, the energy gap is forced open, and the material's internal structure is violently broken down to create a conductive path, like a lightning strike. Now let's bring back our copper atom. Copper is more complex, with 29 electrons arranged in 4 layers. but 28 of those electrons are shielded and locked deep inside the inner shells. Only the last electron occupies the outermost layer. In metals, the valence band and the conduction band overlap. The band gap is zero. The last electron already occupies the conduction band. It needs no extra energy to leave its parent atom and join a vast ocean of free electrons, moving randomly in all directions. This overlap is what makes a metal a conductor. But if copper is good, it is the best? At normal room temperatures, the top conductor is actually silver. Both copper and silver have one valence electron. However, a silver atom is larger, with 5 layers of electrons instead of 4. Its outer electron orbits further away from the positive nucleus. Because the electric pull from the nucleus is weaker at that distance, the electron has higher mobility. It moves to the silver structure with more ease, colliding less often with the atoms and losing less energy to heat. Silver doesn't have more free electrons than copper. It simply has freer ones. This brings us to the real-world design. To achieve the highest electrical conductivity, we would use silver. It is the top conductor in existence at normal temperatures. But using silver for an entire power grid is economically impossible. So we use the second best option, copper. It is the standard for homes and underground cables. But copper has a major weakness. Its high density. Copper is heavy. If we use copper for high voltage overhead lines, the weight would require massive and costly steel structures to prevent them from collapsing. This is why engineers use aluminum for the sky. It has lower conductivity than copper, but it's over 3 times lighter and significantly cheaper. In engineering, every choice is a trade-off between performance and cost. But for an engineer, the materials type is only half the story. Purity is just as critical. Even a 0.1% impurity in a copper lattice, like oxygen or phosphorus, can distort the crystal structure, creating massive roadblocks for electrons. This is why high-end electrical cables use 99.99% pure oxygen-free copper to ensure the path remains wide open. Then why do we find pure gold on the pins of a computer CPU? Many assume gold is the best conductor. In reality, it is less conductive than both silver and copper. However, silver and copper are chemically reactive. Over time, they develop a layer of corrosion, either through oxidation or tarnishing, which acts as a microscopic barrier to electricity. Gold is a noble metal. It is chemically inert and never corrodes. It remains perfectly clean for decades, ensuring the high-frequency digital signals in your machine never face an unexpected barrier. Nature provided us with 2 primary categories: conductors, where the energy band overlap, and insulators, where the energy gap is too wide to bridge. But to build the modern world, engineers needed something more flexible. We needed a material with a narrow energy gap, a state where we could precisely control the flow of electrons, switching it on or off with a tiny pulse of energy, millions or even billions of times every second. This middle ground exists in elements like silicon, but only when we modify their internal structure. This is the master switch of the digital age, the semiconductor. We will decode its internal mechanics. If this video helped you see the world in a new way, make sure to subscribe, like and drop a comment to join our mission. Mastering engineering starts with visualizing the invisible. I'm VastVoltage. See you in the next one.